Hello everyone, welcome back to online lecture series on fluid mechanics and hydraulic machines. We are continuing our topic of viscous flow. In our previous lecture, we have completed till the velocity distribution for viscous flow between two parallel plates. So let's continue from there. So next is just wait. Next is shear stress distribution. So we already have the equation, that is tau is equal to mu into d upon dy, and in previous lecture we have obtained this relationship, that is the last equation over here, and we are going to use it. Is equal to mu into d upon dy minus 1 over 2 mu del p over del x into dy minus y square. So let's differentiate this, and we will be obtaining minus 1 upon 2 del p over del x into t minus 2y. So that is the value of shear stress tau. Now we can copy this work. Over here, and if you note down this formula, you can pause this video and note down this formula, that is of velocity distribution and shear stress distribution. So here you can clearly see that the velocity distribution follows the parabolic curve and the shear stress distribution follows the linear relationship, and the same can be visible over here through the velocity distribution and shear stress distribution. So if you recall, here we were having this kind of curve, as well as here also we are observing the similar trend. Okay, you can pause this video and you can first write down this equation and then you can write down this equation. So these two equations gives you this kind of velocity profile. Now let's move forward to the next theory in the same section here, that is a ratio of max velocity to average velocity. Now we already have the value of u. So let me repeat that u value, that is u is equal to -1 over 2 mu del p over del x into t by minus y square. And if you see now this velocity distribution here, then maximum velocity is obtained at the center where y is equal to t by 2, because if you recall here, if you want to get at the center of this between two parallel plates, then it will be at y is equal to t by 2. So we will be obtaining u is equal to u max when y is equal to t by 2. So u max will be -1 upon 2 mu del p over del x here it will be t square upon 2 minus t square upon 2 is equal to -1 upon 8 mu del p over del x into t square, that will be the value of x. Now our focus should be obtaining the average velocity. So similar to our previous case, here we are considering this elementary strip for the small discharge, that is VQ is equal to U into elementary area, that is equal to T cross 1. So U is already available to us, that is over here. Actually, there is a mistake here. The elementary area, if we see, then it will be dy into 1. Because we are considering a small strip. So what happens here, the cross sectional area, here the total dimension is delta y. So elementary small section will be dy, and the depth inside this is unity. So that's why it is dy into 1. So this equals to minus 1 upon 2 del p over del x. Here we have this values, minus 1 upon 2 mu del p over del x into py minus y square into dy, and here we need to integrate this cube from 0 to t. Q is equal to integration 0 to t b cube is equal to, let me take the constant terms directly outside. Square upon t into y square upon 2 minus t cube upon 3 0 to 2 minus 1 upon 2 mu del p over del x d cube upon 2 minus d cube upon 3. So here we will be getting equal to minus 1 upon 12 mu del p over del x to t cube. So here we have obtained the value of average discharge. Now we require to obtain the average velocity. So the average velocity should be u bar is equal to Q upon area, that is equal to minus 1 upon 12 mu del p over del x into t cube over area will be t cross 1 total area. So here it will be equal to minus 1 upon 12 mu into del p over del x t square. This will be the value of u bar. So average maximum velocity to average velocity ratio u max upon u bar is equal to minus minus 1 upon 8 mu del P over del X T square divided by minus 1 upon 12 mu del P over del X T square. So here it will be 12 by 8. So U max upon U bar is equal to 3 upon 2. So let's copy this work into our main slide. Now let's move forward to our next theory, that is the drop of pressure head. So first we need to copy this figure. Like this. And now we will be studying the drop of pressure head. So U bar we have already, that is U bar is equal to minus 1 upon 12 mu del P over del X T square. So del P over del X is equal to minus 12 mu U bar over T square. So integration minus 12 mu U bar over T square dx. So here and if you take the difference between x2 minus x1, you can clearly see it will be the value L. that is the drop of pressure, and in terms of head also we can write down so that is the pressure drop, and let's copy this word here. So let's move forward with our next theory, that is power absorbed in viscous flow through journal bearing. So here we are having a journal bearing, and a shaft of radius r and a diameter d is rotating between this journal bearing. The gap is filled with oil film having a thickness t. So what happens, the oil here is viscous, so the oil which is near or nearly exactly near the surface of the shaft will be rotating with the RPM same as the RPM of shaft. However, the oil which is near this bearing part will be having zero velocity. So let's begin. So here N is equal to speed of shaft in RPM in RPM. T is equal to thickness of oil film L is the length of oil film. So the angular speed of shaft omega is equal to 2 pi n upon 60, and the tangential speed of the shaft is equal to omega into r, or we can directly put omega into d by 2. So here it will be equal to pi d n upon 60, and now the shear stress value tau is equal to mu into du upon dy. Here let's discuss about du upon dy. As I was telling you that near the shaft the velocity will be equal to the velocity of fluid will be equal to the velocity of shaft, that is v, and near the bearing it will be 0 because of no slip condition, and bottom here we are having t, so it can be written as v upon t, and v here is this, that is tangential speed of the shaft. So we can write down is equal to pi d n upon 60 t. So here we can write down is equal to pi d n mu upon 60 t. So we can write down shear resistance or shear force is equal to tau multiplied by surface area so here is equal to pi d n mu upon 60 t multiplied by pi d l. So finally what we will be getting here is equal to pi square d square n mu l upon 60 t, and then the torque tau torque t will be equal to force into radius, that is let us write down directly d by 2. So this will be equal to pi square d cube n mu l divided by 120t, and we can write down for the power also, where power P is equal to 2 pi n t upon 60 that is equal to 5 n upon 30 into pi square dq and mu L upon 120 t. Are we missing something? No. So we can write down E is equal to 5 cube n square dq mu L upon 60 cross 60 cross t. So that is the end of this theory as well as end of this lecture. Thank you for watching this video.